more. 6, 5, 4, 3, 2, 1. Engine start.
In its gantry at Cape Canaveral, Florida, a Thor-able rocket is ready to carry this weather observation satellite on a new space adventure. Called Tiros 1 for television and infrared observation satellite, it contains the most complete collection of instruments ever assembled to study the use of space vehicles for comprehensive weather observation. The most important of these being two Vidicon cameras, one armed with a wide-angle lens of vast scope, the other with a standard narrow-range lens. Both record on this magnetic tape machine, and on command send their scannings back to Earth. The historic launching of the Thor-able carrying the Tiros 1 in its bulbous nose takes place at 6:40 a.m., a peacetime use of a deadly war missile that promises humanity a new era in meteorology. Graphic animation supplied by the National Aeronautics and Space Administration shows how the last stage of the rocket shot the satellite into orbit. A circular path over the Earth, 50 degrees north to 50 degrees south, between 400 and 450 miles out in space. A flying lady's hatbox that circles the globe every 90 minutes, during which every 2 seconds, the wide-angle lens scans 800 square miles. Recordings it's directed to send back to this receiving station at Fort Monmouth, New Jersey. Another space triumph for the U.S., which is explained to Ike at the White House by Space Agency head Glennon, who produces a picture sequence of the satellite scannings.
Tiros 1 was destined to become the satellite which pioneered a new generation of infinitely more advanced and sophisticated weather satellite systems. The National Oceanic and Atmospheric Administration's Polar Operational Environmental, or POES series of satellites that began with the launch of Tiros 1 now provides systematic global weather observation and coverage 4 times each day, and benefits us in ways that were barely imagined in those early groundbreaking days of 1960. Within hours of its launch, Tiros 1 presented an entirely new perspective on our weather. A panoramic view of the Earth from space was revealed to astounded meteorologists, showing clouds clustered and banded in unexpected patterns.
For the first time, it was possible to describe the cloud systems and see how they moved, and one could then begin to make very precise forecasts of how much cloudiness there would be. Combined with radar, you could then identify areas of precipitation and how fast those were moving. These totally transformed weather forecasting.
A series of polar orbiting satellites were launched throughout the 1960s. Those funded by the National Aeronautical and Space Administration for research and development were called Tiros, and those funded by NOAA's predecessor, the Environmental Science Services Administration, were called ESA. On January 23, 1970, The second generation of environmental satellites was initiated by the launch of an improved Tiros operational satellite, ITOS-1. From December 11, 1970 to July 29, 1976, 5 ITOS satellites, designated NOAA-1 through 5, were sent into orbit. NOAA-1 was the first satellite to bear the NOAA name and the first to be launched after the establishment of the National Oceanic and Atmospheric Administration in October 1970.
From inception, there's a long process to get a satellite up doing its work. First of all, you have to have the idea, then you have to have the science, then you have to build the satellite. You have industries competing, you have to have tenders and things like that. Then there's competition and collaboration between or among agencies. Many agencies may want to do it, some agencies want to contribute, some agencies don't want to contribute. Then you have to get the money. You have to go to Congress and have appropriated millions upon millions of dollars for this very sophisticated machinery. Then, of course, there's a launch, and as one of the people mentioned at a NOAA staff meeting while I was there, there's no such thing as a free launch. It costs a lot of money, and it is a very risky proposition.
There's a period of time when you're not in contact with a satellite. It's a little dicey as to whether you're going to recover and see it or not. As a matter of fact, on the new Tiros N, the very first one we launched, tumbled for 14 orbits, and we thought we lost it. And at the 11th hour, the people in flight control and flight ops captured the satellite on a gutsy maneuver, and sure enough, they stabilized it, and it's been working for a long time. So it really, there you have to take your hats off to the operating people who understand how these things work and are always full of new ideas on how to make them work better.
Today, the nation's environmental satellite system is operated by NESDIS, NOAA's National Environmental Satellite Data and Information Service. Geostationary Operational Environmental Satellites, or GOES, provide national or regional short-range warnings and forecasts, and polar orbiting satellites, such as the Tiros N series, provide global long-term forecasting. Together, they are the most complete and advanced satellite global monitoring system in the world. Approximately 500 miles above the Earth's surface, traveling in an almost north-south circular path, and passing close to both poles, the NOAA polar satellites orbit the Earth 14.2 times per day. The satellites scan the Earth directly below with visual and infrared sensors, continuously transmitting data from a highly advanced array of instrumentation. The operational vertical sounder, for example, provides vertical profiles of temperature and water vapor from the Earth's surface to the top of the atmosphere. An AVHRR, or Advanced Very High Resolution Radiometer, collects and sends information on day and night cloud top and sea surface temperatures, as well as ice and snow conditions.
One of the questions that always comes up is the role that the polar orbiting satellites played in understanding some of the other dynamics that we picked up in other parts of the NOAA, let's call it the NOAA system. Example, the 1982-83 El Nino, which to that point was perhaps the most developed El Nino that had ever been measured. Clearly, we got great understanding from other satellites about what was happening at the equator, or the equatorial levels. But without the knowledge of what ice cover was, what the cloud distribution was in the high latitudes, to couple with that knowledge that came from other satellites, the system would have been incomplete.
Polar orbiting satellites are able to collect data from sensors placed on fixed and moving platforms, including ships, buoys, and weather balloons, then transmit the data to a central processing facility for scientific analysis. The instruments also are able to determine precise locations of moving sensors, allowing wildlife managers to monitor and track transmitters placed on birds and other animals.
Everything that's happening in science now is a function of time and scales. And in terms of looking, if you're looking at what's happening in the ocean, for instance, if it happens to be you want to find out something about distribution of marine mammals or fishes or something in the ocean, these are large-scale problems. And you need to be able to go through and utilize the polar orbiting satellite to be able to get snapshots of all of the aspects of this so that you can look at this larger scale.
The Space Environment Monitor on board today's Tiros can detect the arrival of energetic particles generated by our Sun. This information is used to predict the onset of solar storms that can severely disrupt Earth's communication systems.
The satellites do other functions also. They carry search and rescue facilities, and those facilities have helped save over 10,000 lives. That's a lot of people. It's a wonderful facility to have. I'm a sailor, so I like the idea that there's a satellite up there that can help me in a wide variety of ways. And I'm sure other people who use the ocean, whether it's commercial fishermen or recreational sailors, feel the same way.
POE's sensors are able to assign numerical values to observed conditions, converting environmental factors into quantitative data that can be used for numerical weather forecasting, wind field and ocean current analysis, agricultural frost warnings, severe weather prediction, and research.
No storm can approach the coasts of the United States without being observed. The storms approaching the United States before the onset of satellites were literally a mystery. We had a few ship observations, but that was about all. We had a few aircraft observations, but we were not able to define the character of the storms, how strong they were, how fast they were moving. With satellites, it suddenly became possible to observe storms wherever they were in the world.
I wasn't involved in the first Tiros, and I think the people who pulled that all together really should be proud of their accomplishments. It was a great success, and the follow-ons have outlived their design life by many years, which means the American people really got their money's worth out of that program.
From the very beginning, the scientists from the U.S. Weather Bureau were very excited about the possibilities of the new satellite. In fact, so excited that the first administrator of NASA told them to tone down their rhetoric a little bit. But in fact, the satellite proved to be much more effective and useful than was ever thought. So now, as we celebrate 40 years of the Tiros satellite, we can celebrate the innovation, the new ideas, and this new generation of satellites that we have, and look forward to universal benefits from all the data that will come from this new satellite.
A new generation of scientists and visionaries have been inspired to carry this work forward into the new century, looking to fulfill the vision of universal benefits for all of the world's population.